Now finally, at this reactivity discussion, back to the specs for sure, and we'll talk about so-called elimination. Started off in the last module and the start of this module pointing out that if you take an alkene and you react it up with HX, HBr, HCl, you'll make the alkyl halide in a so-called addition reaction. We're adding the HX across the double bond. Well, there is the reverse of that. If you take an alkyl halide and you remove HX for it, and I've put that in quotes for reasons that you'll see when we talk about the actual mechanism, then you can have an elimination reaction in which you eliminate HX from the alkyl halide, leaving you with the alkene as well. And these elimination reactions are very important reactions in their own right. Just to emphasize what it is, there's the alkyl halide reacted up with the base, and we're going to think about hydroxide as our base, and you pull out the HX and you get the alkene. Quick little mechanistic consideration here, although I'm not going to dwell on it. There will be dwelling on it in separated extension material. Here is our alkyl halide drawn out nicely. Notice I've drawn it in the so-called anti-conformation, at least associated with the H and the X. So the base, in this case hydroxide, comes in from one side. It says to the hydrogen, I've got 2 electrons here just for you. Would you like to make a bond? So the hydrogen will say, yes, please, I'd love to make a bond. So we take those 2 electrons. Now, of course, if the hydrogen's going to take these 2 electrons, it's going to tell the carbon to get lost. So there's 2 electrons here that get used into the double bond, and so this carbon now bonds again to this carbon. This carbon's got those extra electrons, so tells the halide to get lost. Okay, now of course all this happens in one step. Hydroxide in with electrons, electrons there, one step reaction. So although I'm not specifying that, this makes this an E2. It's an elimination E, and it's second order because you've got to worry both about the concentration of the base coming in, the concentration of the nucleophile, and the concentration of the alkyl halide. Now the products of this, well, the OH minus comes in with 2 electrons to the hydrogen. That makes water. 2 electrons go from what was the carbon-hydrogen bond to the carbon-carbon bond, making it now an alkene. And then, of course, in order to have 4-coordinate carbon, if this carbon's got that extra bond there to the second alkene carbon, it's told the halide to get lost as a halide. Now, I very specifically, excuse me, used hydroxide for my example there because I used hydroxide for our substitutions. So if you've been paying attention throughout this whole thing, you'll think, well, hang on a minute. If I use hydroxide with an alkyl halide, I can substitute to make the alcohol. Or if I use hydroxide in the reaction, I can get elimination. 2 reactions, same reactants. And that is indeed an issue. Let's compare them. Substitution, of course, we know that the iodine's better than bromines, better than the chlorines, okay? And of course, we also know, in terms of the carbon, that the less stuff there is around the carbon, the better. So methyl, better than primary, better than secondary, better than tertiary. With elimination, we're breaking the carbon-halogen bond. So again, because the carbon-iodine bond is the weakest, the iodo-alkanes are better than the bromo-alkanes, which are better than the chloro-alkanes for elimination. But let's think about what we're doing in terms of elimination. We're going from an alkyl halide, in which each of those carbons has 3 things around it, to an alkene, in which the carbons have 2 things around them. We're going from tetrahedral to trigonal planar. So that means that the more stuff there is around the carbon, the more it's going to want to reduce what else it's bonded to, the more it's going to want to go from tetrahedral to trigonal planar. So that means that as far as the carbon is concerned, the order is completely opposite. Tertiary carbons, tertiary alkyl halides, really like elimination more than secondary. Primary and methyl hardly do it at all. In fact, methyl can't because there's nothing else on the carbon. Okay, so this is the difference between substitution and elimination. The more stuff you get around the carbon, the less likely substitution is, the more likely elimination is. So that methyl halides will substitute, they won't eliminate. Tertiary halides won't do SN2, they will do exclusively, in terms of second order reactions, E2. Okay, primary, pretty much always substitution. Secondary, you have to really think about what else is attached to it and other considerations. How good is the nucleophile, the leaving group, the things, it's secondary, but what actually is attached to the carbon, and so on. Okay, so yes, you have competing reactions, SN2 or E2, under the conditions we've discussed. The differences between them, though, the less stuff there is around the carbon, the more likely it is to substitute. The more stuff there is around the carbon, the more likely it is to eliminate. Now, it's the last couple of things on our elimination. Let's just think about what if you have more than one possible product, more than one possible alkene, and we apply the so-called Zaitsev rules. Now, Zaitsev was a buddy of Markovnikov. They were at the same institution at the same time. I don't really know if they were friends, but they were certainly both in the same place at the same time, which I think is rather cool. One of them, Markovnikov, of course, studying the reactions of alkenes, Zaitsev studying making alkenes. What Zaitsev found was that the more substituted an alkene is, in other words, the more carbon groups it has around it, the more stable it is. So let's illustrate this, and then we'll talk about the other Zaitsev rule, and then we're done, at least with the reactions of alkyl halides. So let's take my favorite one again, 2-chloro-3-methylbutane. And what I've tried to illustrate here is that here's the chlorine that's going to be eliminated. It has to be eliminated with a hydrogen, but there's actually two types of hydrogen here. There's the hydrogen that is attached over here to carbon 3. There's the hydrogens that are attached to carbon 1. And this red hydrogen on carbon 3 is a different type of hydrogen than the hydrogens on carbon 1. It's attached to a tertiary carbon. These are, of course, attached to a primary carbon. So let's see what happens when we eliminate each of those. First of all, let's eliminate the blue one. So we're going to lose this hydrogen, we're going to lose this chlorine. So we make the bond, the double bond between carbon 1 and carbon 2. Carbon 1, carbon 2. Carbon 1 still has two hydrogens on it. Carbon 2 has a hydrogen, and then it has the isopropyl group here, right there. Okay, so how would we name this? Well, it's 1, 2, 3, 4. We start at this end because the alkene has higher priority than the branches do. So 1, 2, 3, 4. So it's but-1-ene, and then 1, 2, 3. It's got a methyl group on it. So 3-methyl-but-1-ene. And as far as substitutions is concerned on this alkene, there's only one carbon group on it. There's 3 hydrogens and 1 carbon, so we would say it is mono-substituted. Now let's think, instead of losing the carbon 1 hydrogens, let's lose the red carbon 3 hydrogen. Lose that, and we make this. So now if we lose the chlorine off carbon 2, the hydrogen off carbon 3, then our double bond is between carbon 2 and carbon 3. There it is, between carbon 2 and carbon 3. Carbon 2 has a hydrogen, there's the hydrogen. It has the CH3 that I've drawn in blue here. And carbon 3 has effectively 2 methyls on it. One of those, of course, was carbon 4 and one was the methyl off carbon 3. But as far as we're concerned for carbon 3, it's got 2 methyls on it. So there we have this here. Let's name it. We've got 1, 2, 3, 4. Or we can start 1, 2, 3, 4, so it's a but-2-ene either way. If we start here, the methyl is on carbon 2. If we start here, the methyl is on carbon 3. So it's 2-methyl-but-2-ene. Let's look at the substitution on this. The alkene's got 1, 2, 3 carbon groups and only 1 hydrogen. So this means this is the more substituted alkene. It is the better one. So Zaitsev didn't just compare substituted alkenes, he also considered trans or cis. Now, of course, these days we'd say E or Z, but I haven't actually found a book that replaces the old trans and cis with E and Z, so I'm going with trans and cis. Trans are more stable than cis. Now, to illustrate this, let's think about two bromobutanes. So now we don't have any muddling extra methyl groups here. We've just got 1, 2, 3, 4 carbon atoms in a row. Bromine is off carbon 2. Okay, now let's think about what can be eliminated. Well, I've got 3 types of hydrogens here. Carbon 2 is going to lose a bromine. Carbon 2 can double bond to carbon 1 if carbon 1 loses one of its protons. Carbon 2 can double bond to carbon 3 if carbon 3 loses its protons. But now there's 2 different types of hydrogen attached to carbon 3. I'm drawing it red, and then this is sort of purple. Hopefully you can see that. So let's think about these products here. First of all, lose the red one. Well, this gives us this species here, double bond between carbon 2 and carbon 3. So there we are, carbon 1, 2, 3, 4. Okay, you've got both of these methyl groups, because carbon 2 really is bonded to a methyl group, carbon 3 is really bonded to a methyl group. Both of them are on the same side, because what we've done is I've lost, and this is, again, university chemists looking at this will freak out, but it's the best way to show it nicely here. Losing this hydrogen here with the bromine, well, now the methyl group on carbon 3 will move here, and the hydrogen, the purple hydrogen, will move there. So that gives us this picture. Can also, of course, use the one off carbon 1. So that gives us but-1-ene, nothing too significant there. Carbon 1 still has 2 hydrogens left. Carbon 2 has a hydrogen and this isopropyl group left. Actually, it's not an isopropyl group at this point, excuse me. It's got a ethyl group left. So there we are, carbon 2 bonded to this ethyl group. So again, monosubstituted, disubstituted, the but-2-ene would be better than the but-1-ene. But now look what happens if this bromine leaves and the purple hydrogen leave from this picture here. Okay. So again, we got carbon 2 and carbon 3 involved in the bonding. Carbon 2 has that methyl group and a hydrogen, methyl group and a hydrogen. Carbon 3 has a methyl group and a hydrogen. But now if you look at where these things are going to go from, the methyl group will be up there, sort of moving into the space left behind by the purple hydrogen, and the hydrogen will move around there. So now we have the trans geometric isomer, okay, because there's 2 different hydrogens here, and again I'm showing it very, very naughtily and simplistically in 2 dimensions, but it would be the same argument in 3 dimensions. Okay, you've got 2 different hydrogens, the red one and the purple one. Lose the red one, we make cis. Lose the purple one, we make trans. Trans, more stable than cis. So of those 3 possible products, the trans would be the one that is made. So there we are, finished discussing the reactivity of alkyl halides. The last set of movies just discussed the importance of alkyl halides in everyday life, but we're done with the fun chemistry.